continue our discussions on the linear harmonic oscillator problem, and hopefully we have been discussing the harmonic oscillator problem for quite some time now. Hopefully today we will be able to write the final result and the complete solution of the one-dimensional Schrodinger equation corresponding to the linear harmonic oscillator problem. So, we start with the Schrodinger equation, and as we all know that the Schrodinger equation, so let me just summarize everything. d2 psi by dx square plus 2 mu by h cross square. I am sure all of you are familiar with this now. Half mu omega square x square psi of x is equal to 0. So, we make a transformation, psi is equal to gamma x, where gamma is equal to mu omega by h cross. If you do that, the above equation becomes d2 psi by d xi square in terms of the new independent variables plus lambda minus xi square psi of xi equal to 0, where lambda is equal to, where the capital lambda is equal to 2e by h cross omega. Actually, I should write is defined to be equal to. This is also defined to be equal to. Gamma is defined to be equal to mu omega. Then what we did was, first we had defined as independent variable eta, which is equal to xi square. We wrote down that equation, and then we found that the large xi value, large xi behavior is of the form of e to the power of plus minus half eta. So, we said that psi of eta was equal to y of eta e to the power of minus half y half eta, and then we determined the equation that is satisfied by y of eta, and we found that the equation that is satisfied by y of eta is given by eta d2y by d eta square plus half minus eta dy by d eta plus lambda minus 1 by 4 y of eta is equal to 0. So, this is the confluent hypergeometric equation, and the parameter c is half and the parameter a is 1 minus lambda by 4. Now, because this is the confluent hypergeometric equation, we said, and because c is equal to half, the two independent solutions are y of eta, and so therefore psi of eta is y of eta multiplied by e to the power of minus I eta, and eta is xi square. So, this we did in the last lecture carefully. So, the psi of xi, the two solutions are C1, this is one constant, F11 A, that is 1 minus lambda by 4, C is half times xi square, and then e to the power of minus half eta. So, e to the power of minus half xi square. This is the first solution, and both are represent convergent series plus C2 F11, then A minus C plus 1, A minus C plus 1. If you do that, this will become 3 minus lambda by 4 2 minus c, c is half, 2 minus c, that is 3 by 2 into xi square e to the power of minus half xi square. So, we said that this series, although it is convergent for all values of xi, but it behaves as e to the power of xi square. So, for the wave function to be integrable, for to be well behaved, this must become a polynomial. And if you recall the f11 function was 1 plus a by c into eta by factorial 1 plus a into a plus 1 into c plus 1 eta square by factorial 2, etc. So, this can become, sorry, let me write it down. This will become a polynomial only when a is 0, minus 1, minus 2, etc. So, when 1 minus lambda by 4 becomes equal to minus m, that is lambda is equal to 4 m plus 1, that is equal to 1, 5, 9, 13. Only for these values of lambda will this become a polynomial. Similarly, in this case, this will become a polynomial only when lambda becomes 3, 7, 11, etc. Now, let me we had done last time for lambda equal to 1. So, therefore, I can see that lambda can take values 1, 3, 5, 7, 9, 11, 13. So, lambda will take only odd integers. This will imply lambda is equal to 2e by h cross omega. So, this implies that E is equal to n plus half h cross omega. Now, let me write down these two solutions again. So, we had considered lambda equal to 1, let me consider lambda equal to 3. So, let me consider lambda equal to 3. Then what will happen is psi of xi will become C1, this will become F11. If lambda is 3, 1 minus 3 by 4, that is minus 2 by 4. So, this will become minus half xi square e to the power of minus half xi square plus C2, and this will be, if lambda is 3, then this is 0. Oh, there is a xi here, because eta raised to the power of 1 minus c, eta raised to the power of 1 minus c, c is half. So, eta to the power of half, eta is xi square. So, there is a xi sitting there. So, C2 xi F11, if lambda is 3, then this becomes 0, comma 3 by 2 into xi square e to the power of minus half xi square. Now, this series is an infinite series. So, we must have C1 is equal to 0 and the wave function will be, and this will be the F11. If A is 0, then that is only 1. So, the solution is for the eigenvalue psi 1 of xi is equal to some multiple of xi e to the power of minus half xi square. The coefficient, okay, I will come back to that in a moment. Actually, I will put here a factor n's of 2, n's of 1, which is the normalization constant, and I will put a factor of 2, which will become clear in a moment. Let me go beyond this. Let me do one for lambda equal to 5. Lambda is equal to 5, and as you can see, I go back to the solutions again. So, you will have psi of xi, please see this, C1, 5 means 1 minus 5 is minus 4 by 1 is F11 minus 1 half xi square e to the power of minus half xi square plus C2 xi F11. Now this is lambda is 5. So, 3 minus 5 by 4, that is minus 2 by 4 is minus half 3 by 2 into xi square times e to the power of minus half xi square. So, if you see that this is a polynomial, but this is not. So, I must choose C2 equal to 0, and so therefore, the wave function will be, if I write lambda is equal to 2n plus 1, then n here is 2. So, I write psi 2 of xi is equal to some constant, and you remember that F11 function was 1 plus a by c xi square by factorial 1 plus a into a plus 1 into c plus 1 xi 4 by factorial 2 xi square whole square by factorial plus so on. But a is 1. So, this term and the remaining terms all vanish. A is 1 and this is half. So, this becomes a 1 minus 2 xi square. So, this becomes 1 minus 2 xi square e to the power of minus half xi square. I choose the constant here such, I multiply this by a factor such that the coefficient of xi square, xi to the power of maximum, the maximum power n, in this case xi square, the coefficient is 2 to the power of n. So, I multiply by 2 and divide by 2, actually minus 2. If I multiply this by minus 2, then this becomes constant, which I write as n's 2. Please see, if I multiply this by minus 2, then it will become 4 xi square minus 2 e to the power of minus half xi square. This quantity is the Hermite polynomial H2 of psi. H1 of psi is 2 xi. Let me do one more. And that is lambda is equal to 7. Lambda is equal to 7. So, lambda is equal to 2n plus 1. So, n is 3. So, this is the third wave function. So, what is my psi of xi? So, you will have you will have 1 minus lambda by 4, this will be equal to 1 minus 7 by 4. So, this is minus 6 by 4. So, that is minus 3 by 2, and 3 minus lambda by 4 will be 3 minus 7 by 4, which is minus 1. So, I will obtain the solution as psi of xi. Please see this. Let me put the solution here so that you can see for yourself. Psi of xi is equal to C1 F11 minus 3 by 2 half xi square e to the power of minus half xi square plus C2 xi F11, and this will become minus 1 3 by 2 xi square e to the power of minus half xi square. So, this is not this is an infinite series. So, it will behave as e to the power of xi square, and so therefore, the function will blow up. Therefore, we must take C1 equal to 0. So, this function should be removed. So, my psi 3 of xi will be A is minus 1. So, please recall that my infinite series is 1 plus A by C into xi square plus A into A plus 1. So, this will cancel out, this will be 0, C plus 1, this will be 0, and you will have some constant xi into 1 plus A is minus 1. So, minus 1 divided by 3 by 2, that is 3 into 2 xi square into e to the power of minus this thing. So, if I multiply this out, so I will get xi minus 2 by 3 xi cubed. The highest power of xi is xi to the power of 3, and I want its coefficient to be 2 to the power of 3. So, 8, 2 to the power of 3 is 8. So, I multiply this by 12. If I multiply this by 12, actually minus 12. So, what will happen is 2 into minus 12 is minus 24 divided by 3 is 8, and this is minus. So, you get 12 xi cubed minus 8 xi. This is the third Hermite polynomial. Similarly, I will just tell you if I do for lambda is equal to, we have done for 7. So, we have lambda is equal to 9, lambda is equal to 9 means m is equal to 4. So, you have 1 minus lambda by 4 is 1 minus 8 by 4 is minus 2, and 3 minus lambda by 4 is 3 minus 9 is 6 minus 2 by 3, something like 3 by 2, something like that. So, once again, since this becomes minus 2, this series will become a polynomial, this series will not. So, we must take C2 equal to 0 and you will have the solution as psi of xi is equal to C1 sorry F11 minus 2 half xi square. This is a polynomial. So, if you can see that, please see this, sorry. This is A, this is C. So, what will be my polynomial? 1 plus A, that is minus 2 by C, that is 1 by 2, 1 by 2, xi square by factorial 1. So, 1 minus 4 xi square. Then plus A into A plus 1. So, therefore, minus 2 into minus 1 divided by C into C plus 1, half into 3 by 2 divided by multiplied by xi 4 by factorial 2. Next term will be A into A plus 1 into A plus 2, but A plus 2 is 0. So, that term will not be there and all subsequent term will vanish. So, you will have 1 minus 4 xi square plus 2, 2 into 2 into 2, 8. I hope I have done it correctly. 8 by 3 divided by 2, that is 6, 2. So, this will become 4 by 3. You do have to do just patiently. 4 by 3 xi 4. Now, I want the coefficient of xi to the power of 4 to be 2 to the power of 4 equal to 16. So, I multiply the whole thing by 12. If I multiply by 12, so I will get 16 xi 4 minus 48 xi square plus 12 H 4 of xi. In fact, you ask me to evaluate any Hermite polynomial unless it is too big. I know the fact that in any Hermite polynomial there are either even powers or odd powers, and because I remember the confluent hypergeometric function, I can immediately write the polynomial within a multiplicative constant, and I choose the multiplicative constant such that the power of xi to the power of n is 2 to the power of n. So, I leave it as an exercise for you to find out what is h5 of xi, what is h6 of xi. Please do this, and this will help you to understand the solution. The h7 of xi is worked out in the book, but I would like you to find out what are h5 of xi and h6 of xi. The final solution of the harmonic oscillator problem is therefore that the solution is, once again, my Schrodinger equation is d2 psi by dx square plus 2 mu by h cross square e minus half mu omega square x square psi of x is equal to 0. Solutions of this equation exist only when the eigenvalues of the problem are E is equal to n plus half h cross omega, and the corresponding wave functions are psi of x is equal to psi n of x is equal to n's of n h of n of psi e to the power of minus half xi square, where h n of xi are the Hermite polynomials. Some people call it Hermite polynomials. H1 of xi is 2 xi, H2 of xi we have found out, and H3, H4. I have actually found out all Hermite polynomials up to H4 of xi. The normalization constant, that of course it takes a little more algebra. You have to use the generating function. So, that is gamma. You must remember this, 2 to the power of n factorial square root of pi. This is the normalization constant. So, you will have psi m star psi n dx is equal to delta m, and these set of functions are extremely important, and in the domain from minus infinity less than x less than infinity, it is a complete set of functions. These form a complete set of functions, and any well behaved function, any well behaved single valued function can be expanded in terms of this function. That is, any wave function, any function phi of x can be expanded as C n of psi. So, there is a completeness condition also. So, that really completes one of the most important and one of the most beautiful problems in quantum mechanics, and that is the linear harmonic oscillator problem. So, now we have obtained exact solutions of the Schrodinger equation for 3 problems. The first problem was, so we had obtained my time dependent Schrodinger equation is I h cross delta psi by delta t for the one dimensional problem h psi, and h is equal to minus h cross square by 2 mu delta 2 by delta x square plus v of x. So, in the first case, case 1, we considered the free particle problem. We found all values. So, the eigenvalue equation is h psi is equal to E psi. We found all solutions, all values of E to be valid. These are actually the continuum solutions. And what are the wave functions? Psi p is equal to 1 over under root of 2 pi h cross e to the power of I by h cross p x. And what is the most general solution? I will have psi of x t is equal to because these are continuum solutions. So, 2 pi h cross minus infinity to plus infinity a p e to the power of I by h cross p x minus E t, that is p square by 2 mu t dp. And psi x t mod square dx represents the probability of finding the particle in the space dx between x and x plus dx. Similarly, a p mod square dp is the probability of finding the particle, and then you can find out the expectation values and things like that. Then we consider the second example, actually it is example 2, the particle in a box problem. There we had a set of infinite number of discrete energies, n square of E1, where E1 was equal to pi square h cross square by 2 m mu a square. The particle was confined within the region 0 less than a. These are the complete set of functions, and we found that the wave functions were psi of x is equal to psi n of x, and this will be equal to 2 by a sine of n pi by a x. These form a complete set of wave functions in the domain 0 to a, and these are the eigenvalues. And the most general solution of this equation, of the Schrodinger equation, will be psi of x t, as I have tried to demonstrate through the software, psi n f x e to the power of minus I e n t. even for the linear harmonic oscillator problem, you obtain an infinite number of discrete eigenfunctions, just as particle in a box problem. You obtain an infinite number of discrete states. The only thing is, my psi n of for the third example that we worked out, I have been working out for the last 2-3 days, was the linear harmonic oscillator problem, in which the psi n of x was the normalized Hermite Gauss functions, this thing, and the corresponding eigenvalues also we had found out, n plus half h cross omega. So, these are the wave functions and eigenvalues, energy eigenvalues, and then we said that even the classical oscillator, the classical pendulum that you see in your first year laboratory, that corresponds to the superposition of different states, and the solution corresponding to that is described by this particular equation. Now, in the following 1 or 2 lectures, we will discuss one more aspect, but before that, let me mention one, that if there is if I try to obtain the solution of d2 psi by dx square plus 2 mu by h cross square E minus v of x psi of x is equal to 0, then if v of x is continuous and finite everywhere, that is, this is continuous and finite, then psi and d psi by x must necessarily be continuous everywhere, and the proof of this is very simple. Let me rewrite this equation as like this: d2 psi by dx square is equal to minus 2 mu by h cross square E minus v of x psi of x. We are assuming that v of x is continuous and finite. It can have a discontinuity. For example, v of x can vary like this, like this, like this, like this, like this. This can be the variation of v of x. It can have discontinuities, but the value is finite. Now, you may recall that we had told you right in our first lecture, the Dirac delta function was the limiting form of the rectangular function. So, it is a spike, it is a rectangle with an unit area, the width is extremely small, the height is extremely large, so that the product is finite. Now, you remember that we had considered another function, which is the ramp function, that a function is constant and then it has a constant value. The derivative of this function, if you plot, this is 0, this is constant, this is 0. So, it is something like this. So, the derivative of the ramp function, we had shown this to be a rectangle function. Now, let us suppose this value is 0, this value is 1. Let us suppose I make this ramp steeper. I had discussed this in great detail. So, this will become sharper. In the limit of this becoming a step function, the derivative is a delta function. And the delta function, the value of the function at that point is infinity. So, if there is a discontinuity in the function, if a function, let us suppose I have the unit step function which looks like this, its derivative is a delta function here, its derivative is infinite here. So, let us suppose we assume that the wave function is continuous, but its derivative is not. Something like this, we had considered this also. I have a wave function like this, something like e to the power of minus mod x. Then at x is equal to 0, it has one value here, but the derivative here and derivative here are discontinuous. So, let me plot this carefully. I had done this before, that if you plot e to the power of minus mod x, so it will be something like this. This is e to the power of minus mod x. If you plot, let us suppose this is the psi. If you plot the wave function, the derivative of this wave function, so it will have a discontinuity. And so, therefore, the double, this is psi prime, and the double derivative psi double prime will be like this only, but at this point there will be, the value will be infinite, because there is a infinitely negative derivative here, there is a minus jump. So, therefore, if the derivative is discontinuous, then the double derivative has a delta function. So, we come back to this equation and we say that let us suppose psi of x is discontinuous, but d psi by dx is not discontinuous. D psi by dx is psi of x is continuous, but its derivative is not. So, then this is finite and continuous, this is finite and continuous. So, the right hand side is finite and continuous, but the double derivative is discontinuous. So, that is not possible. So, the derivative has to be continuous. And in fact, if the wave function is discontinuous, then its derivative is discontinuous and its double derivative is more discontinuous. So, therefore, if v of x has a step discontinuity, then the wave function has to be continuous at this discontinuity, and its derivative also has to be discontinuous, has also to be continuous, I am sorry. So, the very fact that psi of x and d psi by dx are continuous is a consequence of the fact that the psi of x satisfies a second order differential equation. With this introduction, I will start on a different class of solutions, and that is, let us suppose there is a free particle approaching a potential step. I will try to calculate the probability of reflection and transmission. So, let us suppose that at x is equal to 0, this is my x axis and this is the origin. At x is equal to 0, there is a step potential like this. So, V of x is equal to 0 for x less than 0, and V of x is, let us suppose, V1 for x greater than 0. This is the domain. Sorry, I will write this as V0. I will write this as V0. Now, a particle is approaching, particle like electron or a proton or a neutron, with a certain velocity. So, therefore, the solution, the Schrodinger equation in this region for x less than 0, the solution of this, the Schrodinger equation in this region is d2 psi by dx square plus 2 mu by h cross square E minus V of x, but V of x is 0 in the region x less than 0. So, my Schrodinger equation becomes like this. This I put equal to k square. So, I obtain d2 psi by dx square plus k square psi of x is equal to 0. I can write the solutions in terms of plane waves. So, I can write it down, psi of x is equal to a into e to the power of I k x plus b into e to the power of minus I k x. Now, this represents a plane wave propagating in the plus x direction. This represents a plane wave propagating in the minus x direction. I would like you to think for a moment, why does this term represent a wave propagating in the plus x direction, and why does this term represent a wave propagating in the minus x direction? Maybe most of you are familiar, aware of that. The reason that this is, because in quantum mechanics, as you know, that the time dependence we have taken to be equal to minus I e t by h cross. So, if I replace E by h cross omega, so the time dependence of the wave function is e to the power of minus I omega t. Because of that, this term, the complete term, it becomes e to the power of I k x minus omega t. So, this is a wave propagating in the plus x direction. If in quantum mechanics this was taken to be the plus sign here, then this would have meant a wave propagating in the minus x direction. The question is, in quantum mechanics, could I have chosen that? Of course, we could have. The entire quantum mechanics would have remained the same. I would have been replaced by minus I. That is it. But since in all, you see, the Schrodinger equation is given by I h cross delta psi by delta t excuse me, is equal to h psi. So, I assume a method of separation of variables, and I find that psi of x t is psi of x e to the power of minus I e t. If a minus sign would have been chosen, then this would have become plus I e t. But since the convention is, it is a plus sign here, so there is a minus sign here, and the time dependence is of the form of e to the power of minus I omega t. So, in the region x less than 0, I have two waves, two terms. The first term representing a wave propagating towards the barrier, and of course, there is a reflection by the barrier, which is represented by B. Now, I want to write the solution in the second region. Then the first question that you are going to ask me, is the total energy less than V 0 or greater than V 0? We will consider both the cases. We first consider the case where x is greater than 0, the E is greater than V 0. So, you will have, let me have E greater than case 1. So, this is my case 1 and the case 2 will be E less than V 0. So, my solution is d2 psi by dx square. The Schrodinger equation is 2 mu by h cross square E minus V 0 psi of x is equal to 0. This I represent by k 1 square. So, my equation becomes d2 psi by dx square plus k 1 square psi of x is equal to 0. Again, I will have two solutions. Psi of x is equal to a e to the power of I k 1 x plus b e to the power of minus I k 1 x. And as I mentioned before, because the time dependence is of the form of minus I omega t, this term represents a wave propagating to the right, and this term actually, since I have used A and B earlier. So, let me replace this by C and D. I am sorry, C and D. I have used A and B for this in the solutions corresponding to x less than 0. Now, a wave is propagating in this direction and this potential extends to infinity. So, there is no reason why there should be a reflected wave here. So, therefore, we can write that in the second region, that is for x greater than 0, there cannot be a reflected wave, and therefore, the solution is given by psi of x is equal to c e to the power of I k 1 x. So, therefore, let me write down the solutions in the two parts. I have this barrier, this is V 0, this is x equal to 0. For x less than 0, you have psi of x is equal to a e to the power of I k x plus b into e to the power of minus I k x, and for x greater than 0, you will have psi f x is equal to c into e to the power of I k 1 x. At x is equal to 0, psi should be discontinuous as I had discussed just now, and the derivative also has to be continuous. derivative also has to be continuous. So, we will have at x is equal to 0, the wave function is a into e to the power of I k x plus b into e to the power of minus I k x. So, at x is equal to 0, it will be a plus b is equal to c. So, this is the equation that we get from continuity of the wave function. Then continuity of the derivative will be, if I differentiate this I k, and here it will be minus I k. So, I k a minus b is equal to I k 1 into c. So, we obtain these are the two equations. So, I cancels out. So, we multiply the top equation by k 1. So, I will get k 1 a minus b is equal to k 1 c, and k 1 c is equal to k into a minus b. So, you will have, you take b in this side. So, you will get k minus k 1 into a, and if we take b on this side, so you will get k, I am sorry, this is k a plus b, k a plus b. So, it will be a k minus k 1. So, I have here, I multiply this by k 1. So, k 1 into a, I am sorry, this is. So, I had multiplied this by k 1, k 1 into a plus b is equal to k 1 c, this is equal to k into a plus b. So, therefore, I will bring the b here. So, I will get k 1 plus k into b is equal to k plus k 1 into a. So, this gives me that b by a this is the coefficient, the amplitude of the reflected wave, amplitude of the incident wave. So, this will be equal to b by a will be equal to k. I again made a mistake. So, this is b will be k 1 plus k, this will be k minus k 1. So, b by a will be k minus k 1 divided by k plus k 1. So, the reflection coefficient will be k minus k 1 divided by k plus k 1 whole square. Okay. So, this is one expression. Then we can calculate, let me rewrite this one step more. So, a plus b is equal to c. Okay. So, we will have an I k a minus b is equal to I k 1 into c. So, what we do is now multiply the top equation by k, and I remove the i's here. So, k b appears here, k b appears here, and then I add them. So, the b's cancel out. So, you get 2 k times a is equal to k plus k1 into c. So, you will obtain c is equal to k plus k1 divided by 2k. So, I have then been able to find out the coefficient b in terms of a and obtained an expression for the deflection coefficient. I have also been able to find out the coefficient c in terms of a, which will be related to the transmission coefficient. What now I have to do is, and which I would like to leave as an exercise for all of you to solve, and which we will do in the next lecture, calculate the current density associated with the solution in the second region, the current density associated with the incident wave, current density associated with the deflected wave. And from there we will consider the reflection and transmission coefficient. Before I conclude in the next 1 minute or 2 minutes, we will then consider the case E less than V0. When I consider E less than V0, then there will be not oscillatory solution in this region, there will be exponential solutions. This is something like the evanescent wave which is present there. In optics or electromagnetic theory, when you have a beam coming in here and undergoing total internal reflection, then according to ray optics, the total energy gets reflected. But when you solve Maxwell's equations, then although the energy, the reflection coefficient is 1, the total energy is reflected, but there is an exponentially decaying wave here. This wave is known as the evanescent wave. So, let us suppose this is glass, this is air, and if you put another glass surface here, then there is a possibility, in fact it does happen, through the evanescent wave a beam can leak out. This is in optics, this is known as frustrated total internal reflection, FTIR. In quantum mechanics also, we will show that there exists an evanescent wave, and which will eventually lead to the phenomenon of tunneling. Thank you.